Okay, and now we go to our featured speaker tonight. Our speaker tonight is Dr. Alberto Conti, who has been with the Space Telescope for about 8 years, he tells me. I thought you were here before me, but obviously you came a bit after me. He has worked in several positions while being here. One with the Community Missions Office, doing work on working with other missions and things, and then he has moved over to the MAST, the Multi-Mission Archive at Space Telescope, that he will be telling you about tonight. I don't know where in Italy you got your PhD, but Trieste. That's what I thought. Okay, that's what I was going to guess. That's the easy place to guess, anyways. In Italy, he is a wonderful person, and I'm sure you will enjoy his talk tonight, ladies and gentlemen. Dr. Alberto Conti.
Thank you, Frank. Thank you. Oh, here we go. Thank you, Frank. Good evening, everyone. Please feel free to stop me and ask me questions during my talk. So I'm going to do something a little different tonight for you because, as Frank said, I am the archive scientist at the Multi-Mission Archive. So I'm going to tell you what the archive does. Lots of people see very, very pretty pictures. So in order to get your attention, there are pretty pictures at the end. There's a video at the end where actually he's going to showcase a lot of interesting data that will be released by the archive. And so, but before that, you have to go through a few view graphs which tells you what we do and who we are and why Hubble and the archive are so important. So let me tell you first, this doesn't work. Let's work with this. What is the Multi-Mission Archive? So NASA in 1997 established basically what is a set of archives. And one of them is here, is located here, and is the NASA Optical and Ultraviolet Archive. So we store data from missions like Hubble in the optical, Galaxy, I'm going to showcase this a little bit later, in the ultraviolet, Kepler, which is a mission that we also host, for which we host the data as well, which is a mission that is trying to find terrestrial planets around the center of our galaxy. But we also host missions that are not live anymore, they're not running anymore, like old missions like IUE and FUSE and IUV. So these are all ultraviolet missions. So, okay, sorry about that. Okay, so together with MAST, which is the Multi-Mission Archive at Space Telescope, NASA established other archives. And in particular, they established the archives with which we communicate and we share data most often, which are the NASA Astrophysics Data System, which is basically the archive for publication. So every time we publish data and papers that refer to the data and scientific analysis that talks about the data, the ADS is the place for publications. All the data that Frank just showed you about gamma ray burst is going to be hosted at HISARC, which is the High Energy Astrophysics Science Archive, which is located at Goddard. And again, this hosts not only gamma ray, but also X-ray data. Not all of it, but some of the X-ray data. And then on the West Coast, we have the Infrared Science Archive, URSA, which also hosts a search engine, if you will, for astronomy, which deals basically with infrared data. So what is our mission? So we have to do a few things to do archive well, and you'll see why we have to do it well at the end, toward the end of the talk. But basically, we basically want to lead in providing basically technical solution for archive. And why do we want to do this? Because it's very, very cost effective, as you will see at the very end. There's a lot of research that gets done by archives alone. It was not like this maybe 10, 15, 20 years ago, but now it's actually going to be overwhelmingly dominated by archives, that I will show you in a second. In order for us to be leaders, we need to provide storage, so reliable storage, secure storage for searching missions that are not only the Hubble mission, but missions like any other missions that we have, like I will show you in a second, like Galaxy and Kepler, perhaps. In order for us to enable people to use archive data very efficiently, we need to make use of pretty simple, if you will, and user-friendly interfaces, and allow people to discover tools that are not only located here at MAST, but are located at other archives to maximize the scientific potential of the data. And then to do this, we also want to, as I mentioned at the beginning, develop a good relationship, if you will, with other archives, because they're going to be very important in meeting our bottom line, which is enable new science. At the same time, we have a larger mission, if you will. We are part of the Space Telescope Science Institute, and so our main goal, is really to try to optimize science that is led by the community in general. So we provide a service. All the data, most of the data that we have here at Hubble is freely accessible to anyone. All the data in the archive is freely accessible, so we really want to be those that enable science in the UV and optical. We also like to do something very important to me personally, but also to the Space Telescope Science Institute, which is we need to nurture innovation in science. Why? Because computers are changing, and the way you're doing science is changing. The interfaces to archives are changing. The way we access science is changing. So we need to be able to be the leading edge, to be able to enable new science, and honestly get the best scientists wanting to get data out of our archives to do their science. And then, as again Frank mentioned this morning, you're going to hear from Mark Postman about the new endeavors that we're going to partner with. We are interested in taking our ability to operate, space telescopes like Hubble for 20 years and move on to the next generation, which is beyond JWST. So Mark is going to talk to you about ATLAS, which is again a prototype of what could be after the James Webb Space Telescope. So what is the landscape of missions that we have in astronomy right now? So these are sort of, this is not an exhaustive list, but there are quite a few missions that we have here. So all of these missions in white are space-based missions, and all of the missions right here are ground-based missions. And so all of these missions somehow are related to, to the discovery of, in the case of, for example, of Kepler, of planets, but we also have gamma ray observatories, we have microwave observatories, we have ultraviolet, we have Hubble here, we have infrared. And if you ask how many missions does the Space Telescope deal with among all of these, and actually it's quite a fair number. So these are all the missions that we have somehow an involvement in. We are involved in probably the largest data collection of data that was going to start for astronomy. The laser is dying. Okay. In 2015 or so now, we have, as you well know, Hubble data. We are involved in another very large collaboration called the Sloan Digitized Sky Survey. And just to highlight a few, these are the missions that we store here, so to speak, that for which we provide access. And so some of them are not working any longer, as I said before. Some of them are still working, and some of them are relatively new, and some of them are at the end of their life. So if you go to MAST, the Multi-Mission Archive, this is the face of MAST. So this is the archive, and the archive is just a normal site like any other site, and except when you search here, you search for all the collections of data that we have, which is not only Hubble. I'm going to show you what we have. We also have access. You can search each of the missions. You have some tools that are used for scientists to discover what we have. But also you have access to some software. You have, believe it or not, an archive manual that tells you how to, what the data looks like, if you will. And we also have something which is very important. I'm going to show you why later on, which is these products that we deliver to the community, which are, if you will, science ready. So we deliver a lot of data to the community, and these particular products, which are called high-level science products, don't need to be manipulated any longer. That you can actually do science right away. And that's been, as I will show you in a second, very, very successful. So as I said, we have a manual. So if you're really interested in learning more about the archive and all the gory details, there are many, maybe too many chapters on what you can do. Okay, this is dead. What you can do basically in data archives. You have yours maybe. The bag. Green button there. Okay, thanks. There you go. So anyway, so we have basically it's not, while we try to provide very easy interface, it's not that simple to actually go to the archive. You can search very easily, but then you have to really do your science. You really have to understand what data looks like. So why do people come to the archive, and what are they looking for? So we asked periodically, we do a survey periodically and ask folks to tell us what are the missions that you come to the archive for. And so nobody's surprised to see that 1/3 of the people that come to the archive want Hubble data. I'm going to show you why they want Hubble data and how much of it they want. But also we have very large ultraviolet missions. And so a good fifth of, or a little bit more, come here to get ultraviolet data. Many people, including including many machines, if you will, many other archives, mine what's called the Digitized Sky Survey, which is, if you will, a all-sky survey at relatively low resolution, but all-sky survey that was conducted to basically allow us to point Hubble into and to have Hubble stable basically in the pointing position. So the Digitized Sky Survey is actually 10% of our traffic. And then you have a few legacy missions like IUE and FUSE, and then you have Kepler, which is actually going to increase much, much faster than any other because there's a lot of interest for planets lately. Okay, so if they come here and they look for data from Hubble and Galaxy and so on and so forth, why are they? What are they interested in? Right. So again, this is a survey that we conducted about a year ago, and it basically tells us that most of the people come here to get their data to do their research. This is important to us because it allows us to know that we have to optimize our interfaces and the way people access the data to allow them to actually do their research as fast as possible. Either come here, get their data, and leave, or come here, get their data, analyze the data, or do some little pre-analysis before they download the data and understand exactly what data they want. But the other interesting thing is that you see that this observational support, there's lots of people in-house that are actually doing a lot of quality assurance, if you will, for the data. And actually lots of people in-house use our own archives, which is actually very interesting. And lately, even though it's not as high as we would like, and we are trying to do something about it, there's a lot of outreach and amateurs that are coming. The barrier is right now still the interfaces that are a little too harsh for the non-astronomers. So how many times do people come to MAST? And this is actually something very important. We were not surprised about the results, but it's something we have to deal with. And I'm going to explain why. I'm going to explain what I mean. So if you see here, 2/3 basically of the people come here between a few times a month and a few times a year. That means that we cannot really implement drastic changes to the interfaces that we have because when people come here, they're going to have a learning curve again, and we don't want to do that. So we have to sort of take into account that there are people that are coming here once a month or a few times a year. And so we have to take into account that the interface has to be as easy as possible for them to understand immediately because probably they forgot. So how much data do we have? So I'm going to show you this in a few ways. I'm going to show you how much data we serve. But in reality, I'm going to explain what this HLA means in a second. But a good 2/3 of the data in the archive is actually Hubble data. So this is Hubble Space Telescope data, which is being collected over the last 20 years. But then in 2004, I believe, or 3, a project called the Hubble Legacy Archive was started to basically reprocess all the data that Hubble has observed to make it science ready. And this project is taking a huge portion of our holdings. So how much is it really? So we have about 166 terabytes of data in the archive. So that's twice the size of the Library of Congress, just to give you a perspective. And we also have another little wedge here that shows us, what other missions are. What is, if we remove the Hubble Space Telescope, basically, and these few missions, what are our collections? The interesting thing is that we have this large collection. Again, it's large but not gigantic by modern standards. It's a large collection. But the interesting thing is that we have about 1 million HST observations hosted in the archive. So we have to make these interfaces very, very stable to allow people to search. And I'm going to show you actually a live demo of how you search the Hubble archive. So how many searches are we going through? So we started in 2001 with maybe very, very few searches. But then if you take a look at the progression here, we basically almost double over the last few years. And this is a combination of factors, and it's due to a combination of factors. One is basically the fact that we have more data, which people are very interested in, but also we allow people to search data in a much more meaningful way, in a much faster way, in a way where they can get their data very quickly. And so this spike in searches is the ability for users to ask very, very specific questions to the archive. So give me exactly the data I want and not anything more than that. And this is actually something that is relatively new. You can tell the spike has happened since 2008, and is due to a few interfaces I'm going to show you. I'm going to show you in a second. So this is why the archive is important. So if we take a look now at how much data we put in our archives, this is this blue curve down here. So we basically add to the archive about 15 terabytes every year. And this curve right here represents our ingest rate. So how much data we ingest per year. I'm gonna tell you why there are little bumps in here. The green curve is how much data we deliver to the community. So if you do a little calculation, you basically realize that we deliver 6 times more data than we have in-house. So every year we deliver 6 times the amount of the archive to the community, and this is a huge volume to be handled by the community. So what are these bumps, and why are they important? Well, the first bump is when ACS and NICMOS were when we had service emission 3B. ACS and NICMOS were installed. So before ACS and NICMOS were installed, the data rate was relatively small. It was still pretty large, but it was relatively small. But then ACS is a very large camera, and NICMOS is also pretty large. And so you see a spike here in how much data we ingest, and a corresponding spike in how much data people extract from the archive. Then there's a period where all the instruments are working, but then at some point, some of you might remember, ACS fails. So ACS basically is broken, and we need to wait for service emission to fix it. And so there's a dump, there's a sort of a dip, if you will, in how much data we ingest, because we don't have data from ACS anymore, and we have this valley, if you will, until 2008, when the service emission 4 adds, not only repairs ACS and STIS, but adds 2 new instruments. So the jump is not, we don't go back to 2002 levels in terms of data ingest. We go up much more, and you can see how much more the community is being interested in getting our data. So this is why our archive is very important. I went the wrong direction. Sorry. Okay. So now I'm going to show you a few videos. Before I show you, I started to show you this movie. I have to explain to you what I'm showing you, because it might be a little complicated. So this is the final state of this movie I'm going to show you. So on this axis, I have how much data is available in our archives. So in this case, as of March of 2011, we have about 55 or so terabytes of Hubble data right here. The size of the bubble, the bigger the bubble, the more data we have. This is the Hubble Legacy Archive. This is Galaxy, and so on and so forth. On the y-axis, I'm just counting how much data we give to the community. So I'm gonna run this movie now from 2001 to now. So you see the Hubble data keeps increasing. We serve the community. They move to the left. We decrease the amount of data because we reprocess some data. The Digitized Sky Survey enters. It's a fixed size. We don't increase. That never changes. Galaxy, as you see, it's a very large mission, but it starts relatively slow, and then it moves very fast to serving much more data. And then these are the prepackaged products, which are very useful for the community, and they are being used at a very high level. So this is interesting for us because we actually have a way to quantify how much interest there is in each of the products. And take a look at Kepler. Kepler just entered last year, and is just exploding basically because there's a gigantic interest in taking a look at Kepler data. And again, we host the data, and so we serve a lot of the data. So this is an interesting way to show it, but I think perhaps a little bit better way to show it is to show you a slightly different approach. So this is exactly the same plot, so how much data is in the archive, but now this axis represents how much data we deliver to the community for every month. So you're going to see all these points going up and down according to how much interest there is. And so if I run this movie, you can see that these points go up and down. Hubble is almost constant. It just increases in size, so the bubble gets a little larger. And you see the Digitized Sky Survey. Galaxy is very slow, but Galaxy is just crazy. It just moves very fast, and it goes up and down. And then look at the high-level science product. At some point, both the high-level science products and Galaxy in 2010 or so, they just overshoot even Hubble, which is very interesting. So there's a lot of interest for data releases for these archives that are not the Hubble archive. Does everybody understand this kind of thing? Or it's a little complicated, but it's a nice way that I have to show people that it's also a fun way, I think. But it's a nice way to show people actually how much data is actually delivered to to the community. So part of the importance of having a good archive is also that lots of people, Hubble time, as you will see at the very end, is very precious. So lots of people submit lots of proposals, and you can take a look and ask how many proposals are submitted from where to observe for the Hubble Space Telescope. And the U.S. dominates, as you can tell, but there are actually the Europe is a close second. And this is important because, as I will show you in a few slides, there's a lot of funding that goes with being approved for observing on Hubble, and that funding actually supports a lot of efforts. So this is why archive data is extremely important, because every time we have publications, the number of publications over the last few years, this is only Hubble publications because they are overwhelmingly the largest in the archive. You see, the number of publications grows very, very fast. So we have roughly 800 or so publications that use Hubble data. But look at what happened in the past. So if you just disregard these two lines here, but you look at the blue and the yellow, in the past, people that they're called guest observers, people that actually applied for time of Hubble and got data, were the majority of those that were publishing papers. But this yellow line is telling us that today, people that use the archive, this is people that only use archival data, so they don't apply for time of Hubble, they just come to the archive, get the data, and do their science. These people actually now, and they will eventually take over, and they have in the last few years, they will take over people that can observe on Hubble. And so the archive, to some extent, is going to be the biggest possible legacy that Hubble has. In a sense, it's going to be what really drives research for Hubble and many other missions over the next 15, 20 years, and particularly when Hubble is not going to be flying any longer. Another thing that we can actually ask is, which is I think is very important, is ask how important is Hubble, though? And why are we asking this? Because there's a lot of questions about how much Hubble is funded and how much publications we have funded. Was it really worth it? And so there's a metric. It doesn't really matter what this metric is, but what matters is that if we compare the impact, the technological impact in terms of scientific discovery that a telescope like Hubble has, and we compare it to things that you probably are familiar with, the Voyager and the Apollo missions, and Chandra, which is another space observatory, and GRO, another space observatory. You compare how the impact on science. You see they all lay down here. This blue curve is Hubble. So this blue curve represents the fact that in productivity, basically since Hubble was repaired, you can see this shoots up, Hubble has been the most successful instrument in science over the last 21 years. And this is very, very important because there's a lot of, as I will show you in a second, there's an ecosystem of folks living off of grants and off of projects that are determined by Hubble. And I think that is part of the reason why we are so successful at Hubble has been so successful. So let me recap for a second. So if I take 2 years of Hubble, here's the ecosystem that Hubble produces, so to speak, in terms of archival data, in terms of funding. So we basically give about 55 million or so in support for archival proposals or guest observer proposals to the community over 2 years. We support between graduate students and postdoc about 300 what's called full-time equivalent. So it's like 300 people or maybe people over 2 years. And then Hubble has produced more than 1,400 papers with very, very many citations. And we also produce, as the graph showed you before, a lot of interesting science. So we go to many science. And as a testimony of how successful this instrument has been, not only for scientists, but for the general public, we have about 4 billion hits every 2 years on the Hubble site, which Frank knows very well. Okay, so I'm going to show you for the next few minutes how you really access the archive. And I'm going to use 2 examples, which are among the most, the friendliest and probably the most useful tools that have been produced by the archive. So I'm going to give you a live demo in a second of 2 things. One is going to be the Hubble Legacy Archive, which basically allows you to search very simply data and take a look at where Hubble is observed, and we're going to play with the data a little bit. And these products, as I mentioned before, are products that have been sort of enhanced for the use of scientists. So they can actually be taken as they are, or almost as they are, and science can be done on them. And then the other example I'm going to show you is GALEX, which is the Galaxy Evolution Explorer, which is a UV satellite for which we have the data. And then again, that also has the ability for you to browse data, to do, you're going to see the interface in a second. So let me give you a very quick demo of both. So this is the Hubble Legacy Archive. So when you go to the Hubble Legacy Archive, you can search for any object you like in a Google-like fashion. So let's search for the MICE, which is an interacting galaxy, which is one of my favorite. I like emerging galaxies. And so what scientists do, they search for a particular galaxy, for example, and they see this tabular, if you will, way to displaying data, which is useful to them because they can filter on each of these columns. But then they also can take a look at actually what Hubble has. So these images are being retrieved in real time for you. And you can see we have data here. Each of the images are as they come from Hubble and as they're ready to be analyzed. And then the interesting thing you can do, you can actually say, I would like to actually take a look at this image. Let's see if we can actually do this. And you can see this image. This is an image actually that came from Hubble. And you have the ability as a scientist now to zoom in and out of this image, to change perhaps the contrast, and I'm going to show you why this is important. So, for example, these are two merging galaxies, and what scientists might be interested in, some scientists might be interested in, is looking at, for example, dust in this region. So we can actually zoom in this particular region. Let's see if we can do this. And this is a little noisy. Let me see if I can find a better image for you. Let me find an ACS. So you have the ability to select each of the Hubble instruments. So I'm selecting an instrument which has a better resolution than the one that I just showed you. So here we go. So this is the advanced camera for surveys. You can see the resolution is a little bit better than the one I had before. So this is the galaxy. And let's say that I'm interested in taking a look at this particular area of this particular galaxy. I can actually bring out, if you will, little by little, the dust lanes that are a result of the merger. And then if you bear with me for a second, you will see that as we zoom in, you're going to see interesting things. So, for example, this is a globular cluster. So this is 1 million stars or so that are formed as a result of the merger. There are clusters in here, all the blue. They're very, very young star results of the merger. And what you can do, which is something you could not do before a few years ago, you can actually zoom. Maybe you cannot see it very well here, but you can actually zoom inside in the galaxy and actually see a lot of detail. You can bring out details that you cannot normally see by inverting images, for example. And you can zoom out and take a look at the whole picture of galaxies in this way. Another interesting object, for example, is a very well-studied object by Hubble. Let's go to the antenna, for example. Here. So I have to say that these images are generated on the fly in color. So this image doesn't exist before we decided to browse it. So this is an antenna for it's again merging galaxies, which is among my things. I like when things mash, I guess. And so I like merging galaxies. This is a very well-studied galaxy. So you see all the blue portion of the image are basically shocks that was generated during the merger and has basically give birth to regions of very high star formation. And then you can do the same thing. You can actually change the contrast in this image. For some reason, here we go. It takes a little bit, and bring out, for example, the very central core of galaxies. And you can see much more detail than you are able to see without. So this is actually quite striking. So you can actually do, and everybody can do this. So I mean, I'm just doing it. You can go and find your favorite objects and play with it. The other interesting thing is, I might want to know if Hubble has observed this object and where. So there's another portion of the Hubble Legacy Archive which actually shows me the footprints. So it shows me where Hubble is observed. And so I can actually say, show me all the observations around the antenna. This might take a little bit. Let's see. Maybe not because I filtered. Hang on. I can do this. Yes. Search. Here we go. So each of the colors now represented by here. These are all the instruments available on Hubble, and you can see that I can select or deselect, and I can actually I can actually select each of the footprints, if you will, and decide that I only want to look at WIFPIC 2 areas. And I can select an image now, and the image details for scientists are going to be broadcast here. And if I want to display something of interest, I can just click on the display and take a look at the images. So this is one of the ways in which we allow users to access the archive very quickly. There's advanced features that allows you not only to ask for images that are in color, for example, but maybe for images that are called high-level science product, which are even more advanced than the one I've been showing you. So this was the Hubble Legacy Archive. But then let me show you the second tool that we use. And so let's go to the mice again. This is now we're going to look at very different data now. This data is not optical anymore. It's ultraviolet. And so let me do this first. So did you remember how big the image that I just showed you of the mice was? Well, this is on the same scale. This is how much better Hubble does. This is on the same scale, if you will, and it's observed by a. Let me see if I can load the full resolution image. Here you go. This is on the same scale. These are those two merging galaxies that were so beautiful in Hubble. Well, the ultraviolet is not that nice because the size of the pixel is much larger. But the idea is that we can actually browse this data in a similar fashion. You might recognize the bottom here, which is basically the same sort of grid that allows you. Oh yeah, come back. The same sort of grid that allows you to basically filter your data. And the interesting thing is that we have a very similar concept here, where you can actually browse through your data, and you're not browsing any more optical data. You're browsing now ultraviolet data. And the interesting thing is, you can ask again, like you did for Hubble, show me all the observations that you have in this particular area of the sky. Go away. In this particular area of the sky that were taken by this particular satellite, which is Galaxy. And then in each of these, for each of these images, we have a little more information than we have about Hubble. We have less resolution, so the images are not as pretty, but we have a little more information. And what is that information? Well, that information is that we actually detect objects. So if I ask our service to return to me details about this particular object, and I ask to look for the mice, it will basically draw a circle and tell me I found object A, B, and C, and D, and so on and so forth around this. And most of those are either galaxies in the background or stars nearby these objects. So we have the ability now to do very interesting things very dynamically. We have the ability to filter and take only, for example, the deeper exposures, or take in only objects that we are interested in. If we want to take objects that are only further away from or on the outskirts of our object, we'd actually filter in real time. You can filter this table, and it will filter graphically. So this is the new way that we have to display this UV data, and we have a way to maximize the display. So we have a way to show you the image itself. We have a way for you to say, oh, I'm interested in this object right here, and then we give you, I don't know if everybody can see this, but we give you information about what's available. So as I try to show you, I think there are lots of ways in which you can access archival data. And what I'm going to show you next is it's a movie made by our counterpart in Europe, by ESA, and it's going to showcase something that is actually quite impressive, which is sometimes the normal mechanism to ask for time on Hubble doesn't really work when you want to do very large programs. And so we have 3 large programs, which are called multi-cycle Hubble Treasury programs, that are in the making at the moment. And this will give you a very, very nice showcase, much better than I could have done in the next 5 minutes, about what is available. Let me see if I can turn the volume up.
Hello and welcome to the Hubblecast. Now, observing time on Hubble is a very precious commodity, and it's hugely sought after. That means that when astronomers want to use Hubble, they have to apply for observing time. And in their application, they have to be very detailed about what it is exactly that they want to study and how they're going to do it. Now, this process works just fine for the vast majority of projects, which usually have very focused scientific goals. However, once in a while, Hubble gets used for something much bigger, with much broader scientific goals. And in these cases, the normal way of handing out time just isn't quite enough. 3 such big projects, called multi-cycle Treasury programs, are underway right now, and they're the most ambitious projects to have ever been carried out with Hubble.
The Hubble multi-cycle Treasury programs are on a completely different scale from the telescope's usual work, featuring thousands of hours of observation split over several years. And rather than being tied to the research question of individual scientists, as Hubble observations usually are, the multi-cycle Treasury programs are designed to create a treasure trove of data which can be used by as many people as possible in their work.
For example, the panchromatic Hubble Andromeda Treasury program is working on a detailed map of the nearby Andromeda galaxy, going from its bright core all the way to the wispy end of one of its spiral arms. Andromeda is actually the closest spiral galaxy to the Milky Way, and it gives us an unparalleled view of the structure of a galaxy that is somewhat similar to our own. It's actually quite big in the sky, several times the size of the full moon. But it's so faint that it's barely visible with the naked eye, even on a dark night. For Hubble, though, it's ablaze with stars, and an estimated 100 million of them will have been mapped by the time the survey is complete.
The survey won't just be plotting their position, but taking detailed color information in visible near-infrared and ultraviolet light, something no other telescope can do. Accurately measuring the colors of stars is vital for studying many of their properties, for example, their surface temperature. With this abundance of data, scientists will be making discoveries in the Andromeda galaxy for a long time.
Another of these Hubble Treasury programs is looking far back into the evolution of our universe. And that's the Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey, or CANDLES for short. By scanning large dark areas of the sky with very few foreground stars in them, this survey is looking beyond the confines of our cosmic neighborhood and into the farthest reaches of the universe. They're observing galaxies that are so far away that their light has taken billions of years to reach us. This allows astronomers to study the distant past of our cosmos and how galaxies have evolved over time. Like the Andromeda Galaxy Survey, CANDLES is using Hubble's ability to make detailed maps of the sky across the visible spectrum and into the near-infrared and ultraviolet. From the early galaxies forming, to the emergence of galaxy clusters, to the age of quasars halfway back through cosmic history, CANDLES is going to give us a wealth of information to study some of the biggest questions in cosmology.
The third of these multi-cycle Treasury programs is the Cluster Lensing and Supernova Survey with Hubble, or CLASH for short. CLASH is looking into huge clusters of elliptical galaxies. These have so much mass that their gravity noticeably bends the path of light, a bit like a huge magnifying glass. The lenses can actually help astronomers see distant galaxies that would otherwise be too faint by amplifying the light we receive from them. What's more, studying these clusters is key to explaining two of the big mysteries of modern astronomy: dark matter and dark energy.
Studying normal matter in the universe, like stars or gas clouds, is relatively easy because it emits or absorbs light. However, it turns out that most of the matter in the universe is not in fact normal, but rather so-called dark matter, which doesn't give off any radiation whatsoever. Now, astronomers don't really know what dark matter is, but by looking at how these clusters bend the light from distant galaxies in the background, allows us to reconstruct a map of how the dark matter is distributed inside these clusters. The CLASH survey is also going to study distant supernovae. This is going to probe the expansion rate of the universe and help us understand the mystery why this expansion is accelerating.
In fact, there are already discoveries being made with the first data released from this survey. In April of this year, a new study identified a faraway galaxy imaged by the gravitational lens in Abell 383, the first of 25 to be mapped by this survey. Thanks to the cluster amplifying the light from this distant galaxy, astronomers were able to make much more detailed observations than would otherwise have been possible. And they discovered that the stars in this galaxy were surprisingly old. They must have been born just a few 100 million years after the Big Bang, much earlier than expected.
So, although Hubble is more than 20 years old, it's actually doing some of its most ambitious work right now, building a library of data that will serve astronomers far into the future. And this means that, despite its age, Hubble won't be eclipsed by the next big thing in space-based astronomy, the James Webb Space Telescope, or JWST.
JWST, which launches later this decade, has been designed to answer some of the fascinating questions that Hubble asked. How do stars form? When did the first galaxies appear? What hides in huge dusty nebulae?
To answer these profound questions, the JWST is designed to observe mainly in infrared light. That means that Hubble's ability to see across the spectrum, from ultraviolet through the visible all the way to the near-infrared, is a unique capability that no other telescope will have for decades to come. These multi-cycle Treasury programs are taking full advantage of this, building up a legacy of data that will help scientists to unravel the secrets of the cosmos for many years to come. This is Dr. J, signing off for the Hubblecast. Once again, nature has surprised us beyond our wildest imagination.
So anyway, I thought it was much better than I could have possibly done in a few minutes with the incredible graphics and everything. So as a concluding remark, I think I'm going to quote the PI, the principal investigator for MAST, the Multi-Mission Archive, which is in the end, the Hubble mission will be indeed dominated by archival papers. And before you ask me, yes, we will also be the archive for the James Webb Space Telescope. Thank you very much. If you have any questions, you can go to my website or shoot me an email. Feel free to do whatever. This is actually my website. So, thank you very much.
All right.
Questions?
Questions. Did we get to sing to Follow the Bouncing Ball video?
You want to see it again? I'll show it to you again.
That was just such a Follow the Bouncing Ball video. There should have been a song to go along with it, right?
Oh, true. I don't know. Suggest something. Actually, I think this is a great way to... Oop, not this one. Let's see. Go. Here you go. Actually, this is not... I don't know if people know that the first person who used these graphs is a statistician from Sweden. And he actually created a program called Gapminder to do something like this, and was bought by Google. And he was using it to study UN data on mortality and fertility and death rates and so on and so forth. It's actually a very compelling way to show how things change over time, I think. So, and when I saw this, I thought I had to try with the archive, so I dumped everything I could. The only thing I did was I showed the scale a little bit better because it was a little strange. But I thought, so if you can suggest some music, that'd be good. I don't know. As long as it's not Italian stuff, I'm okay with it. But
all right, real serious questions. Yes.
Is there any access code needed to get into the archive?
You have to know the secret handshake, okay?
No. Actually, if you go to, let's see, I think I did put it here. So you can actually access everything from archive.sti.edu. There you basically can go, or from here you can actually go and there's a list of sites that you can access, which are the Hubble Legacy Archive that I showed you. You can see Galax. There's no access code whatsoever. You can browse. You can do whatever I did. I did this on the net like you would have done. I'm on the visitors network, actually. I could have done exactly the same thing from your home. So no access. It's all public data.
Other questions?
What's the date now? Is it the 14 that the James Webb's going up?
No comment.
You will notice very carefully that the video said launching later this decade.
Yeah,
okay?
It's unclear right now.
That's the official line right now. We can't give you anything further. There will be some discussions over the summer that will firm up make a date a little bit more firm. But at this point, we can't tell you anything more firm.
It's going to be on the dark side of the moon.
It's going to be
No.
beyond the moon.
Yeah.
Beyond the moon, yes.
Way
Way
beyond.
beyond. It's 1.5 million miles away, yes.
Say it again.
It's technically not serviceable by humans, that's correct. We hope that robots someday, perhaps.
Especially if Dr. Grunsfeld has his
Dr.
way.
Grunsfeld has his way, he was going to send a robot, yes, I'm with him. So.
If I don't know the formal target name, is there some directory or list I can go to find out what my target name will be?
There are a few. Let me go back to, for example, HLA. So, for example, I enter here mice, which is really not a target name. It's something that has been associated by the search engines in astronomy. So, if you take, for example, there's another very famous, probably many of you know, the Hubble Deep Field. So HDF is a word that is recognized, for example. So most of the famous targets. I should have done this here. It's not going to take forever. HDF is it's one of the most highly observed missions here. But there's two ways to do it, right? You can either do very famous parts of the sky that have been named, like you said, Abell what?
Abell 383 was what.
So you can just say Abell 383. So any catalog in general. So Hubble has some data, so I can actually see what you with. Oh, really? 3 exposures only? But the other way to do it is, many astronomers do it by coordinates. So if you know the position of the sky, you can actually enter the coordinates. There is a way. There's a search engine for astronomy, which is not too user-friendly. That's why I didn't really mention it here. It's called NED, the NASA Extragalactic Database. And it's not super friendly, so that has basically a list of everything. But astronomers have very many catalogs, right? So there's an NGC catalog, for example. You see many times NGC. Like I could have, instead of typing antennae, I could have typed, see if my memory is okay, NGC 4809? I don't know. No. Okay, I can't remember now. NGC, I can't remember. 4608? I don't know.
I'll look it up on Google.
4608. There you go. No, I can't remember. So it's a little hard. And typically, when people come, they do a search by position. They know where things are, or they know exactly the target they observed, right? And the target they observed are either defined by position, which is hard.
4039.
Aha. 4038. Yeah. So if I do this and I show the images, that should be. Better be. Sorry, better be the antenna. Okay, so you see the image again that we had here before. So the answer is not that simple. But for example, there are very well-known catalogs, NGC catalog, UGC catalogs. You can actually Google that, and then any of those. There are Abell catalogs of clusters. Any Abell number will do, to some extent. Any NGC number will do. So you can try that. But the answer is not that simple. So astronomers we have our directory, if you will, right? And so you can go to the archive manual. That might tell you something. But typically, we either extract it from a catalog or we know the position, basically. So it's not as simple as I wish it could be. But Google might help, actually. And I don't know. Sometimes if you want to search for a particular object, and Wikipedia has a lot of list of galaxies, for example. You can actually go.
All of the standard galaxies that these people would know, the Whirlpool, the
Oh yeah,
Messier
you can.
all of those, will be resolvable. The Sombrero and things.
So M31, it will be recognized as Andromeda, and you see what happens up here. It tells me what. It basically figures out what M31 is. It tells me where it's located on the sky, and then it fetches it. So if you know the position, so all the Messier objects, all the M objects, right, M33 that are being observed by Hubble are present in this pool. So you can go M. You can try them all. M45.
So I have a question. How does it handle solar system objects? You don't have an RA in a deck.
Right now, we're working on it. It doesn't really handle it. Not very well. So you could do this.
Right. Make sure you guys understand that solar system objects
don't
planets move across the sky.
Yeah.
Okay, so they don't have a fixed right ascension and declination coordinate because their coordinates are always changing. So how does a system like this?
But HLA does have a way to do it. So we're starting to do that right now because there are proposals, and I'm involved with one of them, for example, that is trying actually to extract information from solar system objects. So I just typed Saturn up there. So the HLA knows internally.
But you're getting the Saturn Nebula, not Saturn
Exactly. That's what I'm
planet.
saying. It's not the planet, but so the problem is Saturn is embedded somewhere in here. You just have to know. You just have to know how to query from the archive, and you have to be sort of an expert. Right now, there's no way to query because we don't know. When I type Saturn, it really goes to NED.
It's going to go to NED.
Yeah, and then NED has no idea, so it returns some Saturn nebula. So Jupiter, probably there's no Jupiter nebula, right?
I don't know of one.
Well, we're going to see. See, there's no, yeah. So we're working on it because that's a very, very big deal right now. We would like to do that. And Hubble has a lot of images, as you well know, of the planets. So they're all in here. I mean, they're all really in here. So only people like me and other experts on the archives know how to get to them, which is very unfortunate right now.
That's simply because all of the aliens that Hubble has found, and we have to hide them from the public for now.
No, there are no aliens that we've found. So Frank is pulling your leg. I'm trying to find if there was. No, because it goes to net. No, I'm trying to think if there was a way to show it to you right here, but I can't.
Okay.
Sorry.
But can you type Andromeda or Whirlpool or?
How do you spell
Eagle?
whirlpool? Eagle. Mission L. Yeah, let me just spell check it for those foreigners like me. How about Andromeda? Yes. Andromeda. Yeah, that will be result in the same coordinates, as M31. Yes. Yeah. So I mean, the vocabulary is pretty extensive, and it's been worked over many, many years. So you will be able to type your favorite. If you type, actually, I haven't tried this, but if you type Eagle Nebula, you will probably recognize that this is the Eagle Nebula. Yes. So here you go. So it's pretty extensive. So, and this is the Eagle Nebula.
What percentage of the sphere, the celestial sphere, would be available as data in one level or another, or one form or another? In other words, how much of the sky is Hubble or others? DSS, you got everything.
Yeah, but DSS is not Hubble, right? He's asking Hubble. So it depends.
Not necessarily.
Oh, so okay, there are different answers to that. So Hubble is covered maybe less than 1% of the sky because it's very pointed observations, very small observations. You saw the difference in scale when I showed the Galaxy. But Galaxy, for example, it's a UV, it's a whole sky. The DSS, the Digitized Sky Survey, it's the whole sky. The resolution is not as even close to being that of Hubble, but there are many surveys that cover either the whole sky or very large portions of the sky. The Sloan Digitized Sky Survey covers a quarter of the sky. So there are not very many that cover the whole sky at very significant depths, but those are still useful for us. And ultimately, we would like to cover as much as we can. Hubble is like a precision instrument, if you will. So you really want to investigate very, very in detail because of the instrument it has. DSS was used to map the whole sky so the Hubble could point, so we don't need incredible precision. We need to make sure we get the brightest stars. And we have 1 billion sources, so we have 1 billion points in the sky that we can use to point Hubble, and that's why we use, so we need the whole sky. UV, again, we have the whole sky. There's a few others that have significant portion of the southern sky, so it depends on what instrument, really, you ask. That's why it's so important that archives work to pull all this information together. So,
Other questions down front? Yeah.
Do you have any kind of program that extracts information from this to present to members of Congress?
Well, there are a few. One.
Certainly the Davidson metric that he shows you.
But what do you want to present to the members of Congress? Just images like this?
No. Such as information as the relative use of public.
Oh, yeah. The charts I showed you, we present. We have Hubble is funded by NASA, so it's public money. And so very regularly we have committees that come here to assess the state, how we're doing, basically. And so we show the graphs that I just showed you are the same graphs that we show the visiting committees, we show members of Congress, we show anyone who asks, and these are all public too. So we try to keep metrics. It's very important for us to, not only because we justify why the money is being spent, but how it's being spent and why it's so successful. So the Davidson metric was particularly interesting because we didn't do it. And so they came up with this metric to quantify the impact in science and technology. And Hubble, as you saw, it's 10 times better than anything else. We can present it. I don't know if we hope so. I mean, I think honestly, I think it's we've been pretty successful at demonstrating that Hubble is indeed a spectacular instrument. But I think most of them understand, I would say.
Yes. Communication with Congress is not something that Alberto and I particularly do ourselves. Fortunately, I wouldn't want to.
I was in Congress 2 weeks ago.
Actually, I did get to present to Senator Barbara Mikulski last Friday.
There you
go. But it was just showing off my visualizations.
There is so I was part of the congressional visit a few weeks ago. So there's once a year we actually go to Congress and showcase, make a case for why research and development is important, why science is important, why instruments like Hubble are important. So we try. We have 15 minutes of their attention, but we try. So I mean, we are small to some extent, compared to other the medical field or other fields, but still, it's very important. So, at least to me.
Okay. Any other questions before we finish up? All right. I'm going to say it one last time because I got to.
Monday.
Next month, what day is it on? Monday. All right. Monday, June 6th for Nobel laureate John Mather. We'll see you then. Everybody give Alberto one more big hand.